Hello, everyone. I would like to welcome you again to our webinar today. The topic will be design an overmolded plastic part with mold filling analysis. And again, I'm Elvin Xu, account manager in Moldex3d EMEA team. Okay, so let's take a quick look at the table of contents of today's webinar. So first of all, we'll start with a brief introduction about overmolding. And then in the second part, I'll be talking about Moldex3d multi-component molding module, which covers the overmolding. And then I'll share with you a few successful cases from our customers. And finally, we'll come up with a conclusion to wrap up the day. Okay, so now let's swing straight to the introduction. So overmolding. In plastic injection, there are actually several nouns. Overmolding, insert molding, multi-shot sequential molding. So for overmolding, normally refers to plastic part that is injected to cover, or let's say on, another substrate, which is also plastic. And as for insert molding, normally it refers to a plastic part covering or encapsulate another metal insert. And multi-shot sequential molding is multiple injection that is done continuously to combine two or more components together inside the mold. So strictly speaking, these three are a little bit different. But actually, there's also another general standard saying that overmolding actually covers insert molding and multi-shot sequential molding. So for today, we'll be using a little bit more general standard. We'll focus on the plastic substrate and plastic injection. So plastic with plastic insert. Okay. So now let's take a look at some general examples of multi-component molding product, or let's say overmolding products. So first of all, consumer product like shaves and cosmetic packagings, all the shampoo, bottle of the shampoo, shower gel, all these things that you'll see. And to some bigger parts like the automotive components, the door handle of our cars, maybe our front lamp, and then some in-mold assembled products. It can be medical products, or it can be the toys for our children. Okay, so all these, a lot of our daily objects, they are manufactured by an overmolding process. So some pros and cons about overmolding. So a good thing about it is it gives us a shorter production time because it reduced the secondary operation. So we don't need a manual assemble work. So it also at the same time reduce our labor cost. So it saves our cost on the money wise and also on the time wise. And then since we assembled the part inside the mold, it can create a stronger chemical or mechanical bonding between two materials. So if the materials are suitable, they can be remelted and create some chemical bonding. If not, then we can combine them mechanically. And finally, overmolding or product can give us a better product performance. So for example, like let's say it's a screw, and with a rubber-like overmolded part, we can have a better grip of the screw. So it can significantly improve the product performance and make it more user-friendly, easy for our daily job, etc. But at the same time, overmolding process also has some disadvantages, some difficulties. So number one is sometimes it can be difficult to choose a proper material. So we have to know the property of these material and the reaction between two materials and how it is going to end up. And the second is we need a proper process condition in order to create a good overmolding part. Okay, so for example, without a proper temperature, we might not have a strong enough chemical bonding between two materials. We might not be able to remelt the substrate to a certain percentage. Or sometimes, if the temperature is too high, it might cause some damage and potentially some surface defect to our product. So, a proper process condition is actually crucial to an overmolded part. And finally, since there are more factors than as one single injection molding process, more factor needs to be considered for our tool design. We sometimes need to be extra cautious about the tolerance of two different molds. Okay, so that can sometimes be a pretty big challenge. So, with all these difficulties, sometimes it can be difficult for manufacturers or designers to design and manufacture the product simply based on years of experience. Sometimes it's still very difficult, which is why we need software to help us predict and simulate and perhaps come up with a possible solution for our design. Okay, so which is why we'll go to Moldex3d MCM module. So Moldex3d MCM module, it has a powerful pre-processing tool for analysis. So it has a fully automatic, or it can be semi-automatic meshing tool, and also the process set up, the whole workflow is quite simple. And then it support multi-shot analysis, so it's for overmolding, or sometimes more like a 2K continuous injection. These we can consider, and no matter you have a plastic or metal insert, they can be considered in our module. And after the simulation, we have a remelted zone display that helps us to know about what the temperature does to our substrate. Okay, and if we need to consider the fluid-solid interaction between the part and our insert, the substrate, we can also run a cross-shift analysis. So this enables us to know what the second injection does to the first part, whether it's going to cause deformation for our substrate. And finally, we can consider the orthotropic material property. Okay, so let's take a look at the details about each point. So number one, we have a powerful pre-processing tool. So if you have already known something about Moldex3d, we have different meshing tool. We have eDesign and BLM boundary layer mesh, and both mesh supports multi-component molding, overmolding process. And if you want to run the simulation to do the pre-processing in your CAD software, the sync for NX for SolidWorks, for Creo, they all support multi-component molding. And the whole workflow is pretty user-friendly and very straightforward. So when we talk about the meshing part, for overmolding, we have Moldex3d non-matching mesh technology. So for your insert or substrate, the mesh, surface mesh and solid mesh, it doesn't have to be completely meshed with your part or your second shot. Okay, this non-matching mesh technique can significantly reduce our meshing time, because sometimes if your product design is very complicated, it can be quite difficult to completely match the insert and the part. We do have automatic matching technique, but sometimes for a extremely complicated part, and especially in some small feature region, it can be difficult to completely match everything, which is why we have this non-matching technique to shorten the pre-processing time. And also in the process setup, we have one single window. This window for MCM process, so we can easily link the multiple shot. So we can link the second shot with the previous shot, and we can get the data from the previous shot. And later on we'll have a little bit more detail about this point. And if you want to run core shift, it's also in the same setup page. So the whole workflow is quite simple. You can basically set up MCM process in just one single platform. Okay, so like I said, MCM module supports a multi-shot analysis. So for filling, we can simulate the filling behavior and the flow pattern of our first shot, the first shot, and then later on continue the second shot with the already made analysis as our insert for the second shot. And sometimes we'll be able to observe a little bit of flow difference with or without considering the first shot. And also, not just in the filling, also in the cooling stage, since we can get the temperature result of the first shot, we'll be able to spot some temperature difference of the part and also inside the mold base in the cooling analysis. And finally, since we have different filling pattern, different temperature, in the end, we can see a little bit difference in the deformation, the warpage result. Okay, so here are the info that can be passed from the first shot to the second or even third shot. Okay, so the temperature of the first shot will be used in the second shot. So after we finish the first calculation, at the end of the cooling stage, the part temperature will be used as the initial temperature of the part insert in our second simulation. So this temperature will goes to this shot, and there's a very vague feature line over here, but as you can see, this is our insert over here. So this insert will have an initial temperature exactly the same as the end of the first simulation. And then at the end of the second shot, the temperature can be passed on to the third, etc. And not just the temperature, but if you have some orthotropic material property, like different modulus on each direction, or if you're using a fiber reinforced material, the fiber orientation can be passed on. So in the next page, I'll show you. The fiber orientation result can also be transferred to the second shot. Okay, so these might later on influence our deformation of the whole part after the part and the insert, the substrate, are ejected from the mold. Okay, and then both part can be exported into FEA software to run a further structural analysis. Okay, and like I said, we have a remelted area display. So this is the in the previous page we see this is the first shot, and after we run the simulation of the second shot, since on the right side we have the injection point, so on the right we have a higher temperature, and as you can see, because of higher temperature and probably also high shear stress, in this region that is closer to the gate, we have some potential remelt of the substrate. Okay, so this can tell us whether we will have some maybe flow mark, or maybe we can have a stronger chemical bonding between two material. Okay, and also from another part, so you can see when it's closer to the gate region, we have a large area of potential remelt zone. Okay, so sorry, let's go back to this page. So up until here, we're talking about temperature exchange, heat exchange, and also some orthotropic material property. And all these can be done with a simple non-matching mesh technique. But of course, in order to achieve a good simulation quality, even though we're using a non-matching technique, we strongly suggest our users to maintain a similar mesh size between the part and the part insert. Okay, so if we have two different mesh size, let's say the part insert is 5 times larger than the part, I mean the mesh size, then we might have a poor heat exchange calculation. So actually it is strongly suggested that even we're using non-matching, still we suggest users to keep a similar mesh size. Now, that's for non-matching. But if we're using, if we want to run a core shift analysis to understand the fluid-solid interaction between the injected part and the part insert, then we will suggest our users to use a fully matching mesh. And in order to handle this very complicated, complex fluid and solid interaction. Okay, so it can be a metal insert like this earphone jack, or plastic to plastic part like a lot of a medical part, or even you're using IC packaging if we want to consider the deformation of the lead frame. We'll suggest users to use a fully matching mesh, but we will not focus on the core shift part for today. Okay, so these are the capability of our MCM module and what we can do to help you simulate an overmolding process. So now I would like to share with you a few successful cases from our users, from our customers. So number one is the one case from TomTom. Okay, they have this a navigation device, and the product that they are going to simulate is the they call it a tongue. This one that comes with a one small socket over here that can we can put a ball bearing inside, and it can support this navigation panel. And on the other side, it will be attached to either your window uh, or on the air conditioner. Okay, so in the original design, they use a simple one-shot injection, and then in the end, they have this frozen layer. When we look at the frozen layer ratio, they have an extremely low frozen layer ratio on this socket region, which means at the end of the packing stage, most of the melt over here is still at a molten stage. So, which means this region, we might have some potential high volumetric shrinkage, and in the end, it will cause some product defect and probably visible with our bare eyes. Okay, so when we look at the sink mark result, we have a very high risk of sink mark in these region, especially inside this socket for the ball bearing. And this will cause some tolerance issue. So if we have some sink mark over here, it might, when we put the ball bearing inside, it might be a little bit loose, and so we won't have a strong support. Now, if we look at the real shot, the real product, and as you can see over here and over here, they do have some visible sink mark in their mold trial. So then they come up with a revised design. Since this part, the socket region, it has a extremely high thickness, they tried to separate it into two shots. So the first shot will be this tongue, and the second shot will be this ball socket. And as you can see, this is the design for the first and the second shot. Okay. Now the first shot is okay, but then when we look at the second shot, we'll be able to see some potential weld line over here in the middle, since the injection point is over here. So the two melt will each exactly in the middle on the opposite side of the gate. If we look at the temperature, it's actually within an acceptable range. But when we look at the weld line meeting angle, we have some very poor weld line meeting angle, which means basically these two melt front meet with each other when they're basically parallel with each other. Okay, so with this poor weld line meeting angle, it means we might have a visible weld line, and also the mechanical strength will be influenced, so we'll have a higher risk of crack. But then if we look at the sink mark result from the indicator, and also the displacement is basically it's lower than 0.05 millimeter everywhere. So we will not have a visible sink mark. So we have already eliminated the sink mark issue, since we significantly reduce the thickness in this region. So they have now solved the sink mark issue. Now what's left is the weld line issue on the opposite side of the gate over here. So as you can see, for the real part, there's an extremely obvious weld line over here, and might potentially crack after a period of time. So then they come up with another revised design, number 2, which they use a different sequence. They inject the socket first and then put the tongue as a second shot, and then they put the gate exactly in the middle of the socket. So ideally the melt front will go evenly to both edges and there won't be any weld line. So if we look at the filling pattern, as you can see, based on the filling pattern, there won't be any visible weld line for the socket. And even though there might be a little bit mark on the gate side, but then since we'll inject the tongue, and also this is an assembled part, so on the surface we will not see any defect. So now they have solved the weld line issue, they have solved the sink mark issue, and the gate location is hidden on the inside. So basically, with MCM simulation, they have solved all the existing issue for this part. And finally, we just need to double check on the warpage. So this is the displacement of the final design, and all the linear shrinkage is within a reasonable range for the material. So we can say that the product should have a pretty good quality and within the requirement. And also, if we look at the flatness of the tongue of the real part, the original design, it has a higher, wider range of flatness, as you can see. And with the 2 revised design, since we separate them into 2 different shots, the flatness of the tongue is greatly improved. Okay, and then I would like to share with you a second case, also coming from TomTom, and this time is a watch belt, and according to them, this is a little bit of an embarrassing story, because they have published a news. They have launched a global news, and in the news, they have the flow mark that is visible on this product, and which is why they need to fix this problem before actually going to a large production stage. Okay, so this red part is the first shot, and the second shot will be this blue part, and the flow mark happens on the second shot. Okay, so they come up with several different simulation variables, several different possible solutions. Number 1 is with 2 different thickness of the second part. Okay, and then they try with different gate size and also with different gate location, and after different types of product and tool design, they also come up with a possible solution from a manufacturing point of view, which is just the flow rate profile. Okay, so they try to solve the problem with a different flow rate setting. Okay, and with different variables, they come up with a different temperature of their part, and in the end, they come up with a conclusion that a different, actually, it's a thicker part for the second shot, So a thicker second shot and a larger gate, and also a lower injection speed can be quite helpful. So they combine all these three factors and come up with an optimized design. And as you can see, in the original design, this is the region that has higher temperature, which means potentially remelted region, and also means higher shear stress. So with a higher shear stress, higher risk of flow mark. Yes. As for the optimized design, the temperature has decreased for more than 20 degrees Celsius in these regions. And judging by the color, we can also tell that the temperature distribution in this potentially remelted region is actually more uniform. So not just the temperature is lower in general, but also the temperature distribution is a lot more uniform. So judging by the temperature, we can somehow predict that there will be a much lower risk of flow mark. Okay. So then, based on the simulation result, they modified their tool design, they modified the process, and in the end, this is the final product. So the original design gives them a very obvious and visible flow mark over here and on the other side of the belt. Now with the optimized design, on the right, as you can see, there is no longer any visible flow mark on the watch belt. So they have successfully solved the flow mark issue. Okay, and this will be the last case for today. I would like to share with you one case from Farpless. This is a very typical overmolding part. So on top, we have the first shot with a PP material with fiber. And on top, we have a EPDM, and that provides a sealing for the first part. Okay, so it's on these edges, and later on, when this is assembled with another part, this provides the sealing. Okay, so the difficulty they are facing is actually precise dimension for the first part, but more importantly, the filling, which is the short shot issue for their second part. So in order to have a proper filling pressure to prevent flash, they find it difficult to completely fill the part. So they have to fix the short shot issue. Okay, so this is the simulation for the substrate for the first part. And as you can see from the filling pattern over here, it actually matched with their short shot part. Okay, and then they have two different design for the first part in order to achieve the best product dimension. So for the first part, without any ribs on this gap, so without any ribs over here, they have a total displacement around 2.78. Okay, and then another design is multiple ribs in this between this gap, and then in the end, the total displacement is about 2.47, which is about 10% lower than the original design without any ribs. So in the end, they go for this design with some ribs. So now they have decided the design for the first part, and then they move on to the second part, second injection, which is the EPDM injection. Okay, so this is the original design for this sealing for the overmolded part. At the end of the filling analysis, as you can see, we have short shot, and the melt front stops over here and here. And on the right, we have the real mold trial, which is the product that they have problem. And as you can see, we have two red arrow pointing the end of the melt front. So it's over here and here. And basically it matched with our simulation result perfectly. Okay. So then they come up with different thickness for their EPDM part. Okay, because they figure in order to maintain a proper pressure, injection pressure, they can somehow increase the thickness to make it easier for the melt to flow in the cavity. So all they need to do is to get rid of some extra material for the first part a little bit, and then with a higher thickness, larger thickness on the side and also on the bottom, they might be able to fill the EPDM part. Okay, so with a revised design of the second shot, they run another filling analysis, and this time with the same setting, they are able to fill the cavity completely. So based on the simulation result, they modify the tool, and then finally they come up with a product with a complete sealing on the substrate over here, as you can see on the right. Okay, so with film analysis, Moldex3d helps Farpless to solve a dimensional issue and also a short shot issue for the EPDM injection. Okay, so now the conclusion for today. Moldex3d MCM module simulates a multiple components molding process, including insert molding, overmolding, or multiple shot, 2K or even more shots molding. Okay, and between each simulation, the temperature and fiber information of the previous shot can be transferred to the second simulation. So the temperature, distribution, and the orthotropic material property will be considered in the second or even the third shot of our injection. And then for the substrate, we have a possible potential remelted zone that we can be visualized in order to predict a proper chemical strength or mechanical strength, or on the other hand, predict some potential surface defect. And finally, with a different temperature, with different material orthotropic property, it gives us a different warpage. So that can also be considered in our simulation. So we'll predict the warpage due to a property mismatch of different materials, prolonged cooling time, and some unsymmetrical shrinkage based on our part design. Okay, so that will be the end of our webinar session for today, and thank you for your attention.